Okay, so in this section we need to talk about a few new definitions. First of all, concaving up and concaving down. What does it mean for graphs to be concaving up and concaving down? So concaving up means the graph. So here's a graph, let's say, part of the graph. So let me pick a point in this graph and make a tangent. Okay, look. When I make that tangent, is the graph above the tangent or below the tangent? In fact, it doesn't matter what point I pick. If I draw a tangent to it, okay, it'll be above, right? Such curvature is called concaving up. Right? So they're all concaving up, right? So it can be like that, but the graph could also look like this too. So the graph is going down, but still, if I draw a tangent to it, anywhere on this part of the graph is above the tangent. So if we talk in terms of rate of change, this is the tangents represent instantaneous rate of change, right? Instantaneous rate of change, right? And the instantaneous rate of change is represented by this, right? F prime at A. If it is true that F prime at a little bit bigger than A, okay, so a little bit bigger than A, if this is always increasing for all value of A, then we say it's concaving up. Okay? Then it's concaving up. That's the formal equation version, and this is the picture version. Concaving down means the following. Graphically, if you draw a tangent anywhere, look, what's happening to the graph compared to the tangent? The graph is always below. Right? Always below. Okay, so again, if the instantaneous rate of change at any A is greater than the numbers beside it, okay, the numbers that are actually a little bit further to the right, then it's concaving down. Okay. Finally, inflection point. Okay, so inflection point is this. When the graph, so right now, that curvature right there is concaving up. But at some part of those, at a certain point of the graph, it'll change like this. Okay, so that point right there, where the curvature changes, right, curvature changes from increasing to decreasing, or concaving down, so concaving up to down, we call that an inflection point. So IP. Okay, also if it goes concaving down and then up, okay, right there, that point right there, it's very hard to see, but it's there. You know that because the curvature is changing. It's also an inflection point. Let me show you with the tangent here. Okay, so look, if I were to draw it, look, it's above the tangent, but at a certain point, look, see the tangent line? It passes right through. And then afterwards, the graph is below the tangent. Okay, so that point we call point of inflection, the inflection point. So look, here too, it's below the tangent line. But look, as it leans toward there, it just passes right through, right? And then, now it's above the tangent line. Okay, so recall that the second derivative, right? If second derivative is positive, that means the rate of change of the derivative is increasing. This tells you it's concaving up. If the second derivative is negative, it's concaving down. So you have to remember, compared to the first derivative, this tells you it's increasing, right? The rate of change is increasing. That means it's accelerating, right? It's even growing even faster. That's why it's concaving up. The rate of change is decreasing, then it's concaving down. Okay. And if the second derivative is equal to 0, it's potentially, not always, but potentially an inflection point. Potentially. This is kind of like a critical number. Remember critical numbers? How if it's equal to 0, it's potentially local maximum minimum, but it doesn't have to be. It's like that too.